Well, good evening, everyone. Welcome to the December meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. It's a delight to have everyone here. There's, I'm sure, a number of new faces here tonight. We have a terrific program tonight, and we obviously have a very, very special guest. So let's get started, and I'll explain what the roadmap for that tonight looks like. Next slide, please, Chris. Okay, after a brief introduction to me, from me, we're gonna start right away with Bob Burnham, our special guest speaker. We want to get right into that. After his talk, there's going to be a Q&A, a question and answer. We have a microphone, which we're going to be taking to the audience. We also are looking at, because this meeting is streamed live on the internet, and also, by the way, recorded. You can watch it later on if you wish. And also, we're going to be accepting questions from the internet audience as well. So after Bob's talk, we're going to have a short 10-minute break, and we're going to be a little tight on time tonight. So I'm going to really ask if people can stick to 10 minutes. Following that short sort of stretch break and bathroom break, if you wish, we're going to have a segment on the Ottawa skies. Our president, Gary Boyle, is going to be talking about what to see in the December night sky, what's prominent, what's of interest, followed by a very interesting segment from Al Scott on something newsworthy to share with you, and I bet you some of you already know what he's going to speak about. Thereafter, we've got some very interesting member and images and videos to share with you, and I think you'll find them particularly interesting. You remember last month, by the way, I mentioned, for some of you who were here last month, I mentioned there was a fellow who stepped forward and had a mystery object, okay, that he took a video of when he was just outside of Whitehorse. Very interesting story. I'll let him relate to you, but we're going to share that mystery object as part of the video that he's sharing. We have a couple of announcements. We have door prize as well. When you came in, you got a ticket. We're going to be making a draw for those door prizes with that ticket. We're going to call up the numbers. If it matches your number, you can come up and pick up your door prize. Open to everyone, members and non-members. And then after that, we have our annual general meeting. Okay, so our annual general meeting is we do a lot of procedural stuff. We have to do this as part of our charter. We elect our members. We review the finances, how our finances are, our center finances are, updates on various things. Some of you may not be interested in that, and I respect that. So just before the annual general meeting, the AGM as we call it, I'll make an announcement that, folks, if anybody would like to leave at that point, we're fine with that. Also, Bob Burnham will be selling books. So at that point, Bob will start selling books outside. Okay, outside this theater here. Okay, next slide, please. Great year for membership. This year we've got 62 new members. Okay, so wonderful. Is Jerry Gruber, Siegfried Jans, John Short, Donna Short? Are you here tonight? Any one of them? Say yes, if you are. Yes. All right, terrific. Well, welcome, and it's a delight to have you. And all the 62 members that joined this year, thank you very much. We're working on making sure that. So for our club that has about 375 members, 62 is something that we're particularly proud of. So, and we're looking to continually offer value to new members and prospective members as well. Next slide, please. All right, a few words about the RASC. So the Ottawa Centre, for those of you who aren't familiar with the Ottawa Centre, is part of 29 centres in the Royal Astronomical Society of Canada. The Ottawa Centre is the second largest, okay, following the Toronto Centre in terms of membership. The RASC was founded in 1868. Altogether, there's 4,700 members nationally, and really its mission is to really broaden the awareness of astronomy and advance the interest in astronomy through outreach, through education, through publications. Into the community. So our center has a lot of public stargazing programs in the summertime. We have for members lots of things I'll talk about later on, but we feel particularly passionate about it, and we'll be talking about membership after the meeting. And if anybody's interested in finding out what that's entailed, we can explain what that's about. I'll be talking a bit later on. Next slide, please. So members in the news. Okay, we always like to have a short segment of who's in the news. Well, Pierre Martin, who is here tonight, he's our meteorite. I hesitate to say enthusiast. I like to say expert. Okay, he always takes some, and top right picture there. He always takes the most amazing meteor shower images that appears in many publications. And we feel particularly proud that he's a part of our community here. And his work is very impressive. And if you're part of the RASC and some of the other astronomy clubs in town, you'll see his emails and the enthusiasm that he has and his reports that he shares. It's something to see that. So well done, Pierre. Next slide. So many Ottawa Centre members may be a little surprised at this news tonight, and one of our members, who's based in Baja, California, is Mike Wirfs here. Mike is donating his 18-inch Starmaster Dobsonian to our center. So a very, very, very generous gift. So Mike, if you're watching this live from your location in Baja, thank you very, very much. Yeah, it's outstanding. So it'll be a wonderful addition to our observatory that we have. We'll be hearing more about Mike Wirfs later on in this presentation. So next slide, please. Okay, so now I know I'm rushing, but I really want to get right to our feature speaker here. Bob Burnham, many of you know, he's been writing an article and contributing to of course I hesitate right now, to Astronomy Magazine and Discover Magazine for as long as I can remember, the mid 80s. He's a author of many books, some of which he's selling tonight. He's a speaker. He offers astronomy tours of the Atacama Desert, the Northern Lights, and other regions. If some of you have heard him before, he's full of passion, a nice blend of humor too, which makes it nice. And his books, I can vouch for them. It's outstanding books, all right? And I think I want to leave it there, but let's all give Bob a warm welcome and thank him for coming and joining us.
Thank you, Mark. Thank you. Okay. So really great to be here, an honor. Now, Mike and your other overlords who decided on the talk, I offered them 2 talks and they said, well, we like both. Can't you give us both? So I'm going to do something I've never done before, combine 2 different talks. So if it looks a little disjointed and things are thrown back and forth, I'm apologizing in advance because I'm trying this out. Maybe it'll work. Maybe it'll be great. And then this will be a talk that I'll do again. Combining 2 very different topics, light and vision and the universe. What is the universe? And we have another title for it, Where is the universe? What is the universe? Where is the universe? A question that we and everybody else started asking when we were kids. You know, as soon as you, 3, 4, 5, 6 years old, and you start wondering, well, what is this place we were born into? What is this? And that used to be the province of metaphysics or philosophy or religion. And in the last century and more, it's been the province of cosmology, field of studying the universe as a whole. Not cosmetology, that's haircuts and perms, that's something else. And we all have the same images about that. We know the story. Fred Hoyle championed the steady state, and for a while, when I was really little, the steady state and the Big Bang were competing. They were both had about equal number of followers. And finally, when we found the cosmic microwave background, that sealed it in about 1966, sealed the case for the Big Bang. So we have the image of the universe beginning 13.7 billion years ago in an explosion. And on all the TV shows, we have the likes of, I almost said Mike Tyson, but that's Neil deGrasse Tyson. Mike Tyson, they're very different. It'd be interesting to have them both in the ring together, though, wouldn't it? And Morgan Freeman, who tends to narrate everything in life, actually. And we know the story. And the general picture that people have is that we know a lot, We know most probably of the basic picture, even if there are still mysteries to be solved. So what I'm going to do in this 45 minutes or so before we take questions and answers is really back up and look at this kind of afresh at what the story is. It starts by how we know what we know. And it really starts with light, because of all of our senses, you can't smell anything in the universe. That's really good, because there are a lot of smelly places out there. Io, around Jupiter, has a lot of sulfur dioxide and hydrogen sulfide. It's like a dorm room. You don't want to smell the universe. You can't touch it except for those 800 odd pounds of moon rocks. We haven't been able to grab the universe. We can't hear anything in space. That's good too, because the sun, now that we know from the field of helioseismology, new field of study of the sun, that it has rapid pulsations like a subwoofer. And if there was air between us and the sun, it would be deafening. And we can't hear anything in space. So the single sense that lets us perceive the universe is light. And if you ask people in your family, what is light? They probably wouldn't be able to tell you. How is it created? How is it born? I'll bet not 1 in 100 can answer that. Even though it's very simple, light's born one way only. When an electron is the key there, shimmering at a certain distance from the atomic nucleus, if it falls down closer to its atomic nucleus, a little photon is created that then flies off at its famous speed. We still use the old imperial units back in the States, so 186,282.4 miles per second in a vacuum. And that's the only way light's born. Electrons move inward. Simple. Most people aren't aware of it, but that photon that gets created, that's everything. Look at this. Look at this, Mike. Here's an old book about the sun. Because all of our stories start with the sun. What did we know about the sun back 75 years ago when this book was written? Chapter 1, it just says the sun is hot. That's all we knew. There's fire in the sun. It's hot. All right, never. I'm not going to keep doing things like that.
Camera ready.
So the sun, you know, in the core, the middle 1/500th of the sun. There's a sun within the sun. There's actually a few different suns within the sun, but in the innermost sun, the innermost 22% or so, is the place where the fusion is created. All the rest of it, the sun that you see, is only the place where everything, the energy escapes. That's not creating the light at all. A little tiny little ball right in the center, 1/500th the volume of the sun. And mostly gamma rays and X-rays. You know, the center of the sun is as black as coal. It's pitch black in the center of the sun, because there's almost no photons of visible light. It's gamma rays and X-rays. And then as these energies get absorbed and re-radiated by the atoms, eventually you get to visible light. So what comes out of the sun is about a 50-50 mix of what we call visible light and infrared. Now here's the story. As that light hits us, we have sense organs, our eyes, that were designed to perceive that which the sun emits. We can't perceive X-rays. Would have been useless. If we're looking for whether it's a sandwich or our underwear or anything, we wouldn't see it if we were perceiving X-rays, because there's almost no X-rays coming from the sun. So we perceive just what the sun emits most strongly. In fact, the sun's peak emission is green light. And sure enough, that's what the human eye most readily perceives. When light dims and we lose the colors at the edges of the spectrum, the reds and the violets, and all we have left is one color, it'll be green. Actually greenish blue. That was the famous Purkinje shift. Jan Purkinje, same guy who showed us that fingerprints could be used for crime, showed us that the peak emission is yellow-green, but in low light it shifts blueward to the blue-green. That's why many municipalities have painted their fire engines green now. Remember when we were kids, fire engines were red? Maybe not here in Ottawa. Were they always, what color are they here in Ottawa? They're still red, so you see, I'm not doing well in this. But many municipalities are changing them to green because that's what we see most readily. But the fact is that light has no brightness or color. This is the first basic kind of amazing reality that I want to share with you. That light, we know now, are waves of magnetism and pulses of electricity at right angles to it. So if you get a magnetic pulse this way, you get the electrical pulse at right angles to it. Each creates the other. You can't see magnetism, and you can't see electricity. So the actual light out there in the world, what's out there, if you ever wondered what it's like, you know, that old philosophical debate, if you're not around, what color is that if no one's in the room? There is no color. It has no color. It's magnetism and electricity. The real universe is blank, black. So the important thing to realize is that how we perceive color is that we create it. Now you have a venerable member, Roy Bishop, that I've become pals with. We've been in touch for years now, writing back and forth. Great guy. So I can say these wacky things here and use him as support. Most audiences, wait till we get a little later on into this talk. But the fact is that starts out with these invisible waves that hits our retinas, where about 6 million cone-shaped cells of 3 types get stimulated by these invisible pulses that hit the back of our retinas. Then through heavy-duty cables, it goes up to mostly the occipital of the brain in the back, where something like 10 billion cells are dedicated to perceiving the image. And there's about 1 trillion synapses also involved. So this is the heavy-duty machinery. Only 6 million perceivers in the eye and 1 trillion synapses for the perception of it. Now the perception is very important. George Berkeley, for whom the campus and the city were named, used to say that the only things we can perceive are our perceptions. And we only assume that there is an external universe that corresponds with our perceptions. So it's very important to realize that when we see this, for example, this is not the actual color. There is no actual color to the universe. This is our perception. And we might wonder where it's located, because there seems to be a lot of universes out there. Most of us assume this is the external world, where this green thing is occurring, and that there's another set of images in the back of our retinas, you know, the upside-down images that the lens of our eye focuses. So that's another set of 3D stereo images. And then physiology textbooks tell us in the brain is this massive machinery, which is where the image is perceived. So let's look at the image. I mean, there's, let's go to the next slide, actually. Enough of looking at me from my living room. Okay, this will do. So we're perceiving this here. So where is that? There's 3 different worlds. We're going to get to the external universe in a moment, but there's 3 different visual worlds. There is the external world that we assume is outside our bodies. There is images in the back of our eyes, on our retinas. And then there are images inside the occipital lobe of the brain, where we are told is the place that's actually perceived. But we only see 1 image, not 3. So which of those 3 is that? What is the location of the universe, the visual, visible universe? Well, it's obvious that the perception is the only place it's perceived. So there's no escaping, and Roy Bishop, Dr. Bishop, is very aware of this. He writes about it in your handbook, especially when it comes to rainbows, that this, even though language has conditioned us to believe is the external world outside of our bodies, is actually the inside of your brain. One of the pages in your handbook every year says rainbows occur strictly within the skull. So this is within your skull. Our language, our custom doesn't do that. And some people might say, well, of course that's outside our bodies. Here's my fingertips. That defines the edge, the extremity of my body. Forgetting that these fingertips are also in your mind. These aren't your real fingertips. They're just the portrayal of them, both the way you feel them, the way you see them. And they're just as much in your mind as that is. That's no farther from the inside of your brain, this stuff, as your fingers are, or your heart is. It's all occurring in your mind. Now, because this takes a while to really fully let in, even though it's in your handbook every year, I'm going to move on from that, but let's remember that when we're talking about the visual universe, we're talking about something that we create, that it's correlative with the observer. Everything visible. Let's go to the next image, in fact. So the colors we see are, and there's a lot of quirks, you know some of them. One of them is that we only have sensors for red, green, and blue, and so we have to create some of the other colors. Some of you are colorblind. 1 out of 10 men are deuteranopes. You know who you are. Red, green, colorblind. To you, red and green and yellow and white kind of look the same, especially if there's no other cues like different shades. For all of us, yellow, it's very marginal whether yellow even exists. Some books say that the sun is a yellow star. That's, of course, ridiculous. High-altitude balloonists and astronauts have always reported the sun is as white as snow. So why do we see the sun as a yellowish star? Well, that's because the sky is blue. The shorter wavelengths of light get scattered among the atmospheric molecules. They're just the right size for the atmosphere to scatter it, giving us the blue sky. We didn't get the blue sky for free. That blue light was subtracted from the incoming sunlight. Remember when you were a kid and somebody gave you a box of crayons and you wanted to portray the sun? What color did you use to portray the sun? Yellow. So why does the sun look yellowish? Well, because white light, as we know, are a combination of all the colors of light. Look at this. This looks white, but if I were to shake it fast enough, you'd see that it's really red, green, and blue. Ready? See if you can see the red, green, and blue that are the real components of the white light. White light is really red, green, and blue, and then any other colors are just gravy. Once you have the primary colors of light, the rest aren't going to make it any more white. So you have the sun giving off all the primary colors of light. The blue is subtracted on our way to our eyes. It goes to the blue sky. That's a lot of blue light that gets lost on our way to our eyes. And what's left then is a sun that has more red and green proportionately than when it started out. And red and green combined give the human eye the appearance of yellow. I'll prove it to you. Red light, green light. If I were to bounce it off the screen, where I combine them, let's see if you can see any yellow there. Ready? You see any yellow? And that's the only way we see yellow. All the yellow that you think you're seeing in everyday life, if you have a spectroscope, I'll bet some of you do, pointed at a directional signal on your car or any other object that looks yellow, and you'll see that all that's coming out of there is red and green. There's no real yellow, it's just all red and green. Here, I'll show it. There's another demonstration. See this yellow light? I'm going to move this rapidly too. Let's see if you can see that it's really made of red and green. Can you see it? Red and green in that? I don't know if you can see it all the way in the back, can you? So our vision is full of these quirks as well that make up the colors that we see. Next image, please. We also have favorite colors. Anybody here have a red pointer on them? I'll bet you do in this group. If you do, you have permission to point it at the screen. I want you to point it at the screen somewhere. Your red laser pointer. Bet one of you has it. How can you not? You know why? Because this is an astronomy group. You have green pointers. That's why. Okay, good. All right, hold that steady. Hold that steady for a minute. So let's put that in a, and there's a competing, a wimpier one. We're not going to do the male thing here. Point that at this part of the screen. Let's put it in a dark part, and we'll put 3 different colors there. Adults, when asked what their favorite color is, 2/3 of adults pick one color, and we're going to show it here. Raise your hand if you're more attracted to the red. Just raise your hand. Look around, everybody. Okay. Now raise your hand if you're attracted to the green instead. Okay. And then finally, raise your hand if you're attracted to the blue. You see that? That's it. It's always a blue or a shade of blue that surveys show that adults are most attracted to. The rest of you, mention that to your therapist next time. So when we're surveying the universe, that's all we've got. We've got light. Our whole take on the universe is from photons. And of course, with our radio telescopes and our space-borne telescopes that probe into the infrared and the ultraviolet and X-rays, there's still other forms of light. But that's where we get our picture of the universe from. Next, please. And then at low light levels, all right, next. I didn't even know I had that one in there. Yeah, there's the sun. So remember, the surface is just the place where all the energy is escaping. That's not really where it's being produced. There's even another sun within the sun. Everything's changing. You know, we've just learned maybe 15 years ago that 70% of the way from the core of the sun is it acts like a solid ball. Spins as if it were a solid ball, undifferentiated. And only from that point outward is there this differential rotation where the equator spins in about a month. Isn't that crazy? We only have 2 disks in our sky visually. Moon and sun, they both appear the same size, and they both spin in a month? Strange. And then the poles, which have a different spin. So the places where those 2 spins meet, 70% of the way from the center, called the tachocline, that's where its magnetic field is created. That's where all the power and the juice is created. We didn't know about that before. Just as when I was a kid, we were taught that the Earth had a liquid iron core. Remember that? They taught us in school. Earth's core was liquid iron. Beep. That's been changed now too. Now we know that the Earth has a solid little ball of a core the size of the poor demoted planet Pluto that spins faster than the rest of Earth. So we have a Earth inside the Earth, and we have 2 different suns inside the sun. All right, next image. All right, so here's what we could call the prismatic colors, the spectral colors, the real colors. There is no star that doesn't give off all these colors. Every star, and therefore every galaxy, made of the same colors, from red on one end to violet on the other. Any other colors you see in life, purple, magenta, all the others are mixtures or interferences, diffraction, where there's interference of some wavelength with another that produces the sensation of different colors. But these are the ones that we see. And as I said, there's quirks. You know how you can see the true color of the sun, since I told you that the sun is really as white as snow? Well, that's the key word, snow. I've been told that here in Ottawa you are familiar with the concept of snow. Well, on a clear sunny day, look at the color of snow, and what's happening then is the yellowish light of the sun is reflecting off the sun, and the blue light of the blue sky is also reflecting off the snow. So they're recombining. What I'm telling you is that the color of snow on a clear day is the true color of the sun, the color that astronauts see. It's not yellow, so forget that business of a spectral class G0 or a G1 star is a yellow star. I don't know where they get these things from. And then you have these little things saying Betelgeuse and Antares or red supergiants. They call them that, but if you actually matched up a swatch from a paint store with these stars, you'd see that they're only slightly on the orange side of yellow. I used to think that there are no true red stars. Some of you are fond of stars like Y Canem Venaticorum and R Leporis, Mu Cephei, you know, the famous garnet star of Herschel, and blood red stars and stuff. But honestly speaking, those are orange. So I thought that, well, there are no red stars. And then in the southern hemisphere, I hope some of you someday come on our yearly tour where we rent out an entire Andes mountaintop with an observatory and a bunch of huge telescopes to use. And there, the beta star in Crux, Beta Crucis, has a little tiny star next to it, a carbon star, Dy Crucis, which is blood red. It's got a B minus V of, I think, +8 or +11. It's astonishing. So there finally is a red star. It's the only red star, I think. Then when the light fades, you get to other weird things. Our realm, the realm of astronomers, and I suppose cat burglars and others who need dim light. When the light falls below 0.7 Lamberts, we lose first the colors on the edges of the spectrum, and the world looks bluish-green, as Jan Perkinji pointed out. Photographers, cinematographers, artists have always known that if you want to depict a moonlit scene, you'll cut it down a few f-stops, and you'll make it a little bluish. You might have wondered why a natural scene should look bluish-green when the moon is white that's lighting up the scene. Why should a white moon make the scene bluish-green? But that's because all the other colors are there, even in the autumn, the beautiful autumn maples. But all we'll see are the bluish-greens that are present, because all those other colors can't be perceived at low light levels. And when the light's below 0.7 Lamberts, they go, and we're now in a different kind of realm. And because we use that all the time with our backyard telescopes, I'm always surprised that people aren't more familiar with the attributes of scotopic vision, low light vision. Photopic vision, the one that our 6 million cone cells use, is very sharp, 3 times sharper than our 1080p high definition TVs. It's a wonderful vision, starts to work right away as soon as we're in bright light. Has a few quirks, I've mentioned a few of them to you already. But the dim light vision is very special. For one thing, it's colorblind. You see no colors. You know that. You turn the lights low if you're looking around your bedroom and all you have is a night light on or something like that. Everything is monochrome. If you had bright red socks, this isn't a group that would wear bright red socks. The kids wear bright red socks. Let's say you took them off and threw them on the floor at night. This is probably not a group that throws their clothes on the floor at night when they get into bed either. But let's say you did, for argument's sake, and all you had was a night light. It would look gray. The bright red would just look gray, no colors. Second attribute is that the best vision that you get in low light is 2200. In other words, it's blurry. And you can see that. Look around the room when all you have is a night light on or a little light coming through a curtain. And you'll see that your floor that had all the details on the wood is now just one undifferentiated blur. Or if the carpet where you could see every little fiber when the main light was on in your bedroom, now it's just blur. 2200, that's the limit of being legally blind. So you are legally blind whenever you do your astronomy. This is why backyard astronomers with a telescope looking at any galaxy, and this is true of any telescope. Do you know no human being has ever seen color in a galaxy? Because no matter what telescope you use, the light level is still too low. It's going to be shades of gray. But a lot of people with their telescopes say, oh, wait a second, where are the details that those beautiful magazine photographs show? You know, you see galaxies with all those beautiful inter-arm nebulae, all that gorgeous, sharp detail. It's not there. All the galaxies look blurry. We say, oh, can you see that central band in NGC 4565? Yeah, I think I see it. You know, we're easy to please. We say, oh yeah, I see that one. All you can see is a little blur. And the magazine photos, or when we take photos, shows lots of crisp detail. And it's gray. We don't see those gorgeous cobalt blue spiral arms and those campfire orange cores of galaxies. We never see that, it's just gray. So we assume that our telescopes are just too crummy. And we couldn't afford a bigger telescope. And that's why we're seeing this blurry gray image. No human has ever seen that. And once in a while, in fact, just 2 weeks ago, I was at Las Campanas in Chile, visiting one of the largest observatory complexes in the world, one run by the Carnegie Institution, hanging out with the assistant director. We were talking about those few times, once every couple of years, when they actually set up a visible eyepiece for visiting dignitaries, like the president of Chile or president of another country. They actually do that from time to time. And they still don't see detail in galaxies, even then. So nobody has ever seen it. Don't feel bad. So it's a very different kind of vision. You have to understand that. It's gray, it's blurry, and then it can't see deep reds. It's got a sharp cutoff at about 6,400 angstroms. So anything longward of that, it's not that you'll see it as gray, you won't see it at all. The scotopic rod-shaped cells, even though there's about 10 million of them, more of them than the cone-shaped cells, give us an inferior vision. And since the favorite color of the universe is the red at 65, 63 angstroms from H alpha, we do not see, and because most of it is dim, we don't see this. That's why the Orion Nebula looks so different when you take a picture of it than when you see it in person. When you see it in person, you don't pick up that H alpha. You don't see the 65, 63 stuff. You take an image of it. CCDs and film are very, especially gas hypered film, is very sensitive to it. So we get a whole different Orion Nebula. It's a whole different universe when we're seeing it. So our scotopic vision cannot see that. A little demonstration would be Christmas tree lights on a rheostat. I noticed that you guys already have them all up, Christmas tree lights. So if you have a rheostat, turn them down, 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 lower and lower, and you'll notice that the green lights, when they get to a certain point of dimness, turn gray to the eye. The blue lights turn gray, the yellow lights turn gray, but the deep reds never turn gray. They just vanish. There is no gray analog for deep red in our low light vision. That's another thing you should be aware of. Next is a giant hole 1 degree across. That's twice the size of the moon in our scotopic vision. And that's straight ahead because we don't have any rod-shaped cells straight back. Now it's true that when we're using our bright light vision, our color vision, there are blind spots too, but they're only half the size. And the blind spot of one eye never corresponds with the blind spot of another, so you never really get a hole anywhere. But with our scotopic vision, there is a hole. That's one reason why we've learned to use averted vision. I've always wondered why the ancients never reported M44, Persepi, in Cancer as a cluster. Because it's really easy to see it as a cluster. It looks like a blur when you look at it straight on. But all you have to do is turn your attention a little bit to the side while keeping your attention on it. You look a little bit to the side of M44, and it's clearly a star cluster. All the stars pop into visibility, just naked eye. I'm just astonished that throughout all those centuries, the keen-eyed Arabs in the desert, nobody reported it as a star cluster. It's really kind of amazing. So it's another thing to be aware of with our scotopic vision is that there's nothing straight ahead. There's a big hole straight ahead. So those are the defects. There's that, no deep reds. It's blurry, 2200, no colors. Oh, there's even, if you wanted even another defect, there's even one more, and that is it takes a while to get going, as you well know. Dark adaptation, you all know about that. In other words, once you turn the lights off in your bedroom, everything looks pitch black for a while, and then slowly you start to see details because those rod cells need repeated stimulation to work at all, unlike our cone-shaped cells for our photopic vision. So that's the basics. Oh, can we have the next image too? And there's for you colorblind people. If you can see a number there, don't call it out. Well, then you are not a deuteranope. I like deuteranopes. These poor people have been told they're colorblind. It makes it seem that there's something wrong with them. But since, remember, the real universe has no color. So anything you perceive is whatever you perceive. They just see fewer colors than we do. All right, so we do feel sorry for them. All right, next image. And then beautiful aurora. Come with us to Central Alaska too sometime. Do this for the Farmer's Almanac. I've been the astronomy editor there for about 30 years for the old Farmer's Almanac. We have a Canadian edition too, as you well know. And so we, the Farmer's Almanac, can come down to our secret places. If you like the Northern Lights, you cannot do better. We've never failed to see them. We go in March. Now, you know you want to get away from the cold by the time March comes along. All right, next. I'm not doing a good salesman job, am I? All right, so here's a lovely, of course, Andromeda. You all know this. And now you know the kind of visual secrets behind it. But I want to go from here and look at, let's leave this image on because it's so nice. And let's talk about the difference between speculation and what we really know in astronomy. One of the problems is that we know much less when it comes to the universe as a whole than all the TV shows let on. Now, I know you're aware that 96% of the universe is dark matter and dark energy, and we don't know what those are. So we start off, we don't know what those are. We can't picture them. Next, of the universe that we do know, do you know about the amazing discovery early last year by a team at the University of at Berkeley, California, led by Shirley Ho, that the universe, they surveyed 900,000 galaxies, the deepest ever survey of galaxy clusters, and found that space has a perfectly flat topology. And that's never been done to that distance. Not the slightest trace of a curve. When I spoke to a few cosmologists, Rocky Kalb and a few others, they were all starting to come to the same conclusion that we in Astronomy magazine, or at least some of us had for a few years, which is that the universe is infinite in spatial extent. This proves that it's at least much larger, at least 1,000 times larger than we ever thought. We always knew that there's something over the horizon, that at the place where galaxies are receding at the speed of light, we don't know what's beyond that. Beyond that, galaxies are receding faster than the speed of light relative to us. In fact, even the galaxies that we do observe, the farthest galaxies, are now going faster than light. So that's no problem, because they're not being accelerated. Getting accelerated from below the speed of light to faster than the speed of light would be a problem, but it's the space that's inflating. So they're not actually physical objects that are being forced to move faster. So we always knew that there was this horizon beyond which we couldn't see. The question is, how much of the universe can't we see? This tells us there's at least 1,000 times more, and using Occam's razor, the universe is probably infinite. You can never prove infinity. You can never prove it's infinite, but that's the way it's headed. So now we have a problem of trying to picture this. We can picture most of the universe as it was, the 96%, because we don't know what dark energy is and dark matter. And now we have the fact that the universe is and if it's infinite in spatial extent, if we assume, and this would be an assumption, but we're assuming that the matter density, energy density per cubic parsec is the same everywhere, it means that the galaxies really go on and on. Like when we were kids, we asked our parents, and maybe we said, hey, do the stars just go on and on? And of course, they didn't know, so they said maybe, oh yeah, they just keep going on and on. And, well, they were right. So, but the issue here is, what do we do with this? We can't picture an infinite universe. Nobody can picture infinity. We can't picture what dark energy is. We know that it means that the empty space is inflating. But the problem goes deeper than that. We've always visualized the universe as being in a matrix of time and space. Big Bang happened a certain amount of time ago. And we picture objects, like a galaxy, separated by empty space. Now, we've known that it's not really empty for some time. Emptiness had a bad rap with the ancient Greeks. They hated the idea of emptiness because they were such great logicians. They said there can't be nothing anywhere because the verb to be and nothingness contradict each other. It's like saying I'm going to run, not run. And the church hated it too. They said if God is omnipresent, you couldn't have a vacuum. So if you were pro-vacuum, you were a nut job in the 18th century, let's say, or 19th century. The Michelson-Morley experiment, and then later Einstein's first theory in 1905, showed that, for a long time it was supposedly a plenum or an ether that filled all of space. It bothered a lot of people because how could the planets be traveling through this ether without the slightest resistance? It would have to be a substance that offered no resistance. So Einstein did away with it by showing that light can travel through nothingness. It doesn't need a medium the way sound does. So we did away with the need for it, but we've recently found that space is not nothing after all. First of all, beyond the 1 atom per cubic centimeter of material, that's what we normally say. It's a hard vacuum, there's only a little bit of substance in space, but there's a lot more. There are fields, magnetic fields and electrical fields. There's neutrinos. Do you know that 1 trillion neutrinos go through each of your fingernails every second? And I don't mean that they only go through fingernails and not the rest of your body. There's photons everywhere filling empty space, and since matter and energy are equivalent, that's something. And then the biggie is vacuum energy, first really postulated or proven in 1948 with Casimir's discovery of the Casimir effect, which most physicists attribute to vacuum energy. Some call it zero-point energy. In any case, every little bit of empty space seethes with an amazing amount of energy, so much that the one estimate is that every little mayonnaise jar, you use mayonnaise, right? Every little mayonnaise jar worth of empty space contains enough energy to boil away the Pacific Ocean in 1 second. And it's also responsible for the particle pairs, particles and antiparticles, that constantly pop into existence and then subside again throughout the universe. It's almost as if the emptiness of space seethes with so much energy it can barely contain itself. This may also be part and parcel or the entire dark energy that makes space have a repulsive force that is pulling the galaxies farther and farther apart. So space is not empty. Secondly, space may not exist on another level, in that we've known now increasingly since 1998 that particle entanglement is real, EPR correlations. Those of you who study this stuff, you know that if you get 2 bits of light or even clusters of material that are born together, they can fly off and live independent lives, but they both know exactly what the other is doing. So that if one is observed, bothered, meddled with in any way, it will materialize. In other words, its wave function will collapse. This was work from John Bell in the 1960s, who said that electrons and other subatomic particles aren't really there. They only exist as probabilistic bits of wave functions, and they collapse to become a real object upon observation. So if one is observed, its entangled twin will also collapse in exactly the same way, showing complementary particles. The amazing thing is, even if they're separated by the width of a galaxy, if one particle is observed and it becomes an actual object with a certain property, let's say a horizontal polarization or an upspin or what have you, the other one will instantaneously, in real time, know that this has happened. It will know it. It doesn't require light speed for the information to travel from this part of the galaxy to the opposite part of the galaxy. It's in real time, simultaneous. It will know it happened and do the complementary thing. This strongly suggests that on some real sense, there is no separation between objects in the universe. So where is space then? Next, Einstein showed us that the gap between anything and anything else is not fundamentally real, but changes depending upon the local gravitational field or how fast you're traveling. If you headed toward the star Procyon at 99% of the speed of light, instead of it being 11 light years away, it would now only be about 2 light years away. Why? Because something warped in your mind? No, because it now is 2 light years away. And if you could travel just under the speed of light, perfectly allowable by the laws of physics, the entire universe would only be from here to here. Shine a flashlight up at the sky, turn on the flashlight, and the moment you turn the flashlight on, that moment, those photons are already at the farthest edges of the universe. Travel at the speed of light, and you'd find yourself everywhere in the universe at once. This isn't theory, this is fact. So where is space then? Where's the gap between objects? So for all these reasons, although we visualize the universe as objects separated by certain amounts of space, there are many reasons to believe that space is not a real thing. You can't take it to a lab and analyze it like a tomato. And time is the same thing. Very few physicists these days believe that time is an actual object. Newton did. He thought it was a real dimension that objects exist in. Immanuel Kant was among many who said, no, it's just something that we devise in our minds, a way of structuring the universe, making sense of the vast avalanche of electrical signals in our brains, organizing things. Time doesn't have any real reality. And sure enough, all of Einstein's equations, quantum, all the equations in quantum mechanics, even Newton's laws, all of them are time symmetrical. None of them need time. The only argument for time's existence would be the second law of thermodynamics, where order tends to go into disorder, like the drawer in which you keep your underwear. See, that only happens in one direction. It never starts out messy and then gets orderly by itself. It only go one way. So that's an argument for the existence of time. But several physicists have told me in the last 10 years, no, it isn't. It just means things are randomizing in the here and now. There's no need for arrows of time. So time, and if time is only a structure that we do and not an actual thing, then of course it couldn't be traveled. There's no reality on its own. There'd be no such thing as time travel. So space, we've seen at least 4 reasons. There are even more. In other ways, space may be only gaps that we organize, again, as part of the animal spatiotemporal organizational system, where based on color or utility or shape, we call objects and their gaps between them space. Inside the sun, would you say that's outer space, under the sun's surface? Many of us wouldn't, but it's very empty there. Between atoms and within its atoms, that's outer space, that's empty space. But we don't think of it as space. So a lot of it is organizational as well. What I'm saying is that our structure of visualizing the universe is based on space and time, largely. And when we see what these things really are, when we realize the universe has no visual characteristics without us as observers, it leaves us with a little bit more humility. The present models are essentially mysterious, and that's the important thing that we have to realize. It's not a pessimistic view of astronomy, because in many areas we're making so much progress. Planetary geology, galactic structure. We know that Mars rotates in 24 hours, 37 minutes, and 23 seconds. That's not going to change. A century from now, we won't revise that by a second. We know the moon is 2,160 miles in diameter. We know that its period around us is 27.32166 days. Those things are as good as gold. But when it comes to the fundamental questions. It's kind of paradoxical. The things that kids would ask. Basic questions about the universe. What is this place? Was it born? Or is it eternal? What's it made of? We've already seen we do not know what 96% of it is. And if it's infinite, what do we really know? My friend Debbie Elmgreen, who used to be president of the American Astronomical Society, she just retired last June, recently told me, when I was talking to her, I was going to write an article about this, and I did. She said, well, we have 200 billion galaxies within view. That's enough to keep us busy for a while, even if it's only a tiny fraction of the real universe. But she slightly misspoke, because if the universe is infinite, as the evidence is pointing, what is within view is not a tiny fraction of it, because any fraction of infinity is zero. So our sample size is essentially zero. Now you're not going to hear Neil deGrasse Tyson talking about this stuff. So what we really presently know, I mean, if you really want to be honest about the universe at large, is extremely little. Our data is tiny. You know that old joke about engineers? Some of you are engineers, so I know you know this, that if you want to make a nice graph, a presentation graph for a group, and you want a nice straight line in some direction to make your point, if you want a nice straight line, use only 2 data points. Well, here we don't even have 2 data points. So the truth, and the bigger question is trying to visualize this and convey this to ourselves and to others. How do we picture infinity? We can't. And it's not just that the new information is doing this. We've gotten used to the Big Bang because it's repeated. We hear about Big Bang Theory. You know, Fred Hoyle coined the phrase pejoratively in the late 40s. He said, oh yeah, the universe started with a Big Bang. It was a joke. But is that really an explanation? When I used to teach college physics and astronomy, sometimes the students would say, excuse me, what happened before the Big Bang? What was the universe like? And if I were in a tired, lazy mood, I'd say to them, well, you can't ask that question because there was nothing before the Big Bang. And if there's no change, if there are no objects that are changing, you can't speak of time. So there is no time if there's nothing changing. So the question is meaningless. And they'd buy it. And they'd say, oh, I see, okay. And they'd sit down. When the truth is, we have no idea what things were like the Saturday before the Big Bang. Everybody knows you can't get something from nothing. You can't get a universe from nothing. So the explanation for this universe that it popped out of nothingness, and we don't know why. Oh, we don't know. So we have ideas. So the current cosmology is model-based. Model-based. We have these various models for how it could happen. They're ideas, and because undergrads and physicists will only make a name for themselves by coming up with a new model that will change the old one, whether it's meta-universes or membranes, brains, and other things, with maybe some math evidence behind them, will change. And it does change every 5 or 10 years. But these are models based on very, very little data. This wouldn't be a problem if everybody realized that our models are only starter models right now, because we have so little data, and that we will be revising them. Unfortunately, most people think that this whole thing, the thing about the Big Bang and the rest. Also, what is the Big Bang if the universe is infinite? How can you have a birth to something that's infinite? How do you get from there to there? You can't. So it means that the Big Bang was just a local event in the hood. That's something that happened in our neighborhood. Maybe there's a lot of other Big Bangs that are going on simultaneously. We don't know because you can't speak of the stuff you don't know. Just as people often ask, this is the most common question that astronomers get asked, what is the universe expanding into? If it's expanding, you've all been asked that, I'll bet. And the mistake there is that everybody's picturing the universe as if it were a balloon blowing up. So if that's the whole universe, what is it expanding into? And the reason there's no answer to that is because, number one, there's 2 reasons. Number one, there's no such perspective as seeing the universe from the outside. Seeing it as a balloon expanding would mean you're outside looking at it. It doesn't exist. You can't be outside the universe by definition. So you've set up a non-existent vantage point, and that's why you get an unsatisfactory answer every time, because the question makes no sense. And secondly, if the universe really is infinite, then you also can't be outside the universe and ask that question. Either way, it's not visualizable, and this is the point that I want to get to. Our symbolic language system, the way we speak and think, even use math and science, is based on duality, symbols. The word water is not actual water. And in the phrase, it's raining, the word it doesn't even correspond to anything at all. We have language that only serves a purpose if it's something we've experienced before. If we say this ball, Mars, is spinning at a certain rate, it's because we know what a ball is like. The planet is shaped like a ball, we can picture it. But when we come to the things that we're dealing with now, with the cosmos, infinite spatial extent, infinite inventory, a Big Bang that has a predecessor that's totally unknown. We can't picture something before there was anything. These are not visualizable. And 96% of the universe being unknown, dark energy, we're left in a realm that we can't even form images of, let alone convey to other people. So the challenge is perhaps coming up with new models, perhaps coming up with a little more honesty. You know, the ancient Greeks, they knew it was hopeless. They'd drink their wine and they'd laugh and there was no problem. So you can go that route. And as I say, it's not a pessimistic thing, because in all the ways we love, this is why I love observational astronomy. We look at Copernicus, 3 days after the half moon. And you see those beautiful terraced walls on the side and the double-peaked mountain in the center casting a shadow on the crater floor. Crater's what, 64 miles across, about 100 kilometers across. Gorgeous thing. We know the heights of the mountain and stuff, and it's real. None of this abstract stuff. Many of my physicist friends hate string theory. They hate it because even though the quest is noble, we're trying to figure out what's behind the 4 fundamental forces. Why do we have only 4 forces? Electromagnetism and gravity and the strong and weak forces within atoms. So the idea has some mathematical basis. Then on the tiniest levels, a trillionth of a trillionth of a trillionth of a trillionth of a trillionth the size of an atomic nucleus, you have one-dimensional strings, and depending upon whether they loop together or connect or stay straight, you can have the forces. The problem is, it doesn't work. For it to work, you need extra dimensions there to exist, of which there's no evidence for any of them, not in our senses or nowhere else. In other words, the 3 dimension of space and 1 perhaps of time won't work. So you have an extra dimension, and then maybe you can make the math. Oh, that doesn't work. We need another extra dimension. Latest, you need 8 extra dimensions. Now, there's no experimental way you can prove this, and there's no observational way. You can either find these extra dimensions or prove or disprove string theory. So many more old-fashioned physicists are saying, back when I was a kid, if you weren't doing observations, not doing experiments, and it was not falsifiable, no way to find if it was real or not, what do you have here? Other than keeping a lot of grad students busy and a lot of departments and universities busy. These are brilliant people. They tend to spill food on themselves in buffets, I've noticed. But they're brilliant people. But is this mind stuff? There's a lot of stuff that works on paper, like the square root of -1, that has no analog in the real universe. So because you can come up with it here doesn't mean it's real. So we're in a funny realm right now. I'd say in a unique place that we weren't at. Even 3 years ago, I wouldn't have said the universe is infinite. 15 years ago, we still didn't know that EPR correlations or entangled particles are real, which shows us that space is not a real separation on a fundamental level. The beginning of this year, I was talking about this, and I suddenly had a revelation at the lectern. I realized that if space really has no fundamental distance, Einstein showed us this, as I've told you, there's no separation between anything and anything else in other frames of reference. If you travel at a different speed, if your gravity is strong, there is no real size to the universe. And I realized that all my life I was picturing the universe as huge, vastly huge. It brought you to humility, thinking of how big the universe was. And I suddenly realized it's not huge or not huge. It's sizeless. The universe is sizeless. So it's an amazing time, but let's be, I guess what we take away from this is to be really honest about what we know and what we don't know. It has an awesomeness to its own with this. And I don't think we do any good by having the TV shows where they're spouting on and they're always in front of like fancy equipment. And it gives it a patina of validity. And the numbers we do know are always to several decimal points. That also does it. The Big Bang happened 13.7 billion years ago, and the cosmic background is 2.73 degrees. And it sounds like we're getting a handle on this stuff. Let me see if there's something else. I know it's time to go to questions before they get the hook and just pull me out of here. Did they ever do that? Did you even have vaudeville here? You probably did, right? I mean, this isn't Mongolia, right? Oh yeah, this gets even, since we've gotten so crazy, let's just go one more level of craziness before, I leave you, and that is with the whole Einstein level of locality. And Einstein really believed that an object's only influenced by its vicinity. A leaf will only blow if wind is blowing on it. A leaf is not going to move because of something on the other side of the galaxy. But the quantum world, the EPR correlations are showing us that an object can actually be influenced. Part of the book Zoom, that's right, books. Mike's going to handle them, even take checks at the break. Zoom, the new book, look it up on Amazon or the New York Times, and I brought a cheap one too. For those of you who've spent all your money on equipment like Bob, who drove us here. And then there's a little strange universe taken from my columns in Astronomy magazine, where I expanded about 25 of them into them, a nice cheap paperback. So I'd say the farthest out thing that we're coming down the quantum pike is the idea that we as observers are intertwined with the universe. We've already seen that everything you see is inside your brain, actually within your skull. Talk to Roy Bishop about it. He'll tell you. But beyond that, since our observations, you know about the double slit experiment. If you don't, look it up. You know that what we see is dependent on the observer. Now, this is producing kind of some freaky things. We've had a physicist who tell us that an object is not a real object until it's an observed object. Nobel laureates have said this. So the idea is that perhaps the universe and the observer are correlative. That we're not just here freakily by accident, and that if we weren't here, the universe would carry on. That in some fundamental sense, consciousness and the universe are correlative. And that perhaps the real nature of the universe is one that involves awareness or consciousness. It's the biggest mystery, consciousness. And when we're trying to figure out what the universe is, we can't ignore it, because everything we observe is on the screen of our perception or our awareness. Paul Hoffman, who was my editor-in-chief at Discover magazine, he left to become the publisher of the Encyclopedia Britannica. So I'm telling you that because smart guy, right? He would always say that the greatest unsolved mystery in all of science is that of consciousness. We don't know what it is. We don't know how it arises. Even an individual baby born, let alone as a human race. I mean, how do insensate, dumb bits of carbon and hydrogen and oxygen in the universe just plunging into each other, how do they ever end up as that Japanese guy who always wins the hot dog eating contest? You know, how does dumb oxygen and carbon develop a taste for hot dogs? You know, the smells and sights and perceptions, our thoughts. This is how we perceive the universe. We'd love to know, because maybe just our consciousness biases what we see and perceive. Maybe we need to know what this is, what this movie screen is, if we're really going to understand what this universe is. But unfortunately, it's a really deep mystery. We don't know how it evolves. You know, you could take all the amino acids and throw them together. You know, the idea is that all of them, you put them in a blender, amino acids for 1 billion years, and then out pops golden retrievers and Vivaldi and all the rest. It's a big mystery. How awareness, this business of awareness, how do you get a dumb universe, Pluto, dumb planet? How do you go from that to awareness, smells of lawns being cut and stuff like that? It's the biggest, of all the mysteries that I brought to you, it's maybe the deepest of all. And yet, until we have that one down, we're also not going to really understand what's going on, especially now that more and more quantum experiments are showing that we as observers influence what happens. So there's some connection there. I'm not suggesting anything to you, any real answers, unfortunately. I'm just giving you some of the questions, some of the mysteries that hopefully we'll be working on. Okay, let's take questions. Maybe we can turn the house lights up a little bit. I love the question part because we can go in any direction. Feel free not to stick with what, please don't stick with what I've been talking about. Go in some other direction. Yes?
In your December article, 2001.
Can you give them the mic so we can? All right, I'm going to repeat the question. Go ahead.
Okay, in your article way back circa 2001 December.
In my article circa way back 2001 December, as if I'm going to remember this thing. I don't even remember what I did last weekend. Yes?
You were mentioning about black holes and singularities, that black holes take infinitely long to create.
Yes, that black holes take an infinitely long time to create. That's what I said in that article.
So in other words, when you look at a black hole, it's not really there.
Right.
Could you explain that?
Yeah, that's another misconception. You'll see it here and there that black holes are forming and materials falling in and then black holes are forming. In truth, a black hole can never form, ever, because the last bit of infalling star material that would create this black hole breaks off from our universe. There's different frames of reference. This is what Einstein was really big on in his second theory, general relativity, in 1915, is that our perspective, anyone outside the event horizon of the black hole, which is the whole universe, sees those final infalling bits of star stuff that would have created a black hole, an event horizon, a singularity, take infinite time. So it's not really a black hole, it's a frozen star. That last material is slowing down and coming to a stop. And a full black hole can never form in our universe because it would take infinite time. And infinite time has not yet elapsed. So you simply cannot have any black holes forming. The objects that we're observing are almost black holes. For example, at the center of our galaxy, Sagittarius A star is a 4 million solar mass amount of material that's close enough to a black hole for us to observe all the movement of the stars in its vicinity that are doing what we're seeing. But a real event horizon, a singularity, can't happen. So we've been saying that in Discover magazine since the middle 1900s. It seems not yet to have reached popular public awareness, but it's quite true. Other question? That scared everybody off. Okay, back there. Yes. There's no, don't be shy. There's no such thing as a stupid question in astronomy. Why do I say that when I know that's a lie? That's not true. You know, in 1994, you had it here too. We had a partial eclipse that was very deep. It was an annular eclipse down in Albany, and maybe you remember that on May 10th of 1994. And on a radio station, I was warning everybody not to stare at it without eye protection because it was only partial or annular. It would hurt your eyes. Dangerous to look at without proper eye protection. And a woman called the station and said, if the eclipse is so dangerous, why are they having it?
I got a question.
So that's what I really should be saying, is that you can't top those, you know, so don't be shy, rather than that there's no such thing as a stupid question. I'm talking about honesty here in this whole lecture, so I have to practice it myself.
Yeah, I got a question here.
Yes, go ahead.
Yeah, you mentioned you were connected with, you'd written for Astronomy magazine.
Where is this voice coming
Right
from?
here.
Oh, okay. Hi.
So I kind of got two questions.
Yes.
One is, do you know Brian May of Queen? I think he's on the editorial board. And the second thing is, do you know what he's up to? I think he's done studies of gases, dust, interstellar gas. Do you know anything about what
He's on the editorial board of which magazine?
Astronomy.
No, I know everybody there. Brian who?
May.
No. Oh, you don't mean Bob Noya?
No, he was in Queen, and he's,
Oh,
I think
no.
he's the chair.
No, I don't know. It's been actually 2 years since I've been out there to Wisconsin, to the offices, so I don't know. Is he new there? I've never met him. Okay. All right, any question that's better than do you know so-and-so? Yes.
Did you like the movie Interstellar?
Did I like the movie Interstellar? Not really. I really loved Gravity, but Interstellar really bugged me. First of all, you had these people. It's going to be a spoiler. Can I do this? No. I shouldn't do this. All right. If you don't want to spoil it, close your ears. I'll just be one part of it. They're on a planet. It was really cool that they said that this planet has such a strong gravity that we're going to age differently than people back Earth. So we have to be really careful because every hour we spend down there, a decade is going to pass on Earth. Our kids are going to grow up. We don't want that to happen. Of course, they go down there, and you know how things go. Nothing goes right, and they end up spending all afternoon there, and sure enough, 30 years passes back on Earth. Problem is, to have that kind of time differential, you'd have to have a gravitational field that would be lethal, not a gravitational field that you could walk around in. But it got worse. You have one of our characters, I won't tell you who, one of the characters goes into a black hole willingly, has all these crazy adventures, and the next thing you know, he's in a hospital, and they say, oh yeah, we rescued you, we found you, and you were in space, we found you. And this is a savvy guy, a smart guy. He never stops to ask him, excuse me, but how did you rescue me from inside a black hole? Exactly, how did that happen? There's not a word. You know, in the Star Trek thing, at least they'd offer some nonsensical thing. They'd go, Scotty or Data and Geordi, they'd say things like, well, if we focus the particle beam and change the deflector shield so that it changes the tachyon pulse from a negative to a positive oscillation, I think we can escape from the space-time warp. And they'll go, make it so. And you go, okay, you know, I'll go along with that. But here they went into a black hole and nobody says a word about how they got out of the black hole. Not even the nonsense words, nothing. So there's enough of that stuff that, whereas with the other movie, I don't know how you felt about Gravity, but that was fun. I thought that was fun. I also love to have a movie there were no villains, you know. The only bad thing about Gravity, you know the bad part? They did a lot of good things, is that when the George Clooney character and the Sandra Bullock character are holding each other, you know, she's trying to rescue him, and they have this tension on these cables, and then they're like this, and he's being pulled away, and they're in space, and he's saying, let go of me, save yourself, let go of me. And he finally ends up cutting the cable so she can live. Well, you know, once they had reached equilibrium, the two of them in space, they could have just let go of each other, and nobody would have drifted away. So he didn't have to die there. So I don't know if I was alone in the movie theater saying, no, you don't have to do that. Don't cut that cord. You don't have to do that. But you know, you make some allowances for some of those things. Okay, other question back there?
That movie was so bad, I'm giving one away as a door prize tonight. There it is.
Which movie?
Gravity.
Gravity was so bad. He's giving it away as a door prize. Okay, well. How many people here saw and liked Gravity? I want to see if I'm alone here. See? All right, you got plenty of people who will be glad to take that gift.
I liked it
Yeah.
for the visual effects.
For the visual
Like
effects.
you're saying, astronomers are saying,
Okay. Yes.
Once I read in a book that it said the universe, there's a possibility that the universe just may be a tiny place in like an even bigger world, but that's only a possibility and a small theory. Is that true?
Well, maybe you can say it's true. It's like it's an old wonderful idea. Remember at the end of Men in Black, the idea essentially that the whole universe is just an electron that's part of a pickle on a sandwich on a plate in a deli on a much larger universe. You know, there's layers. This is it's a nice old idea. Who knows? Who
One
knows?
more question? Right at the back.
Right, I can yell. It's fine. Okay, so you're a fan of observational cosmology. Are there any experiments upcoming that you are particularly interested in, and why?
Oh, I'm a believer in observational astronomy, things we can actually sink our teeth into. Not that theory is wrong. It's just that it would be nice if there can be falsifiable in some way. Somebody's going to make up a theory. Give us a way we can find out if it's true or not. That's all I'm saying with these. Okay, so what do I find fascinating? What would I like to do? The same thing all of you would. Wasn't Rosetta great? And the Philae lander? Yeah, I don't care if the harpoons didn't work and the retro rockets didn't work. That was kind of a little bit of a bummer, but still, it was fabulous. And 10 years ago, the Cassini to Saturn. And next July, we're going to have Pluto visited for the first time. These are fabulous things. What would we like to see happen? All of you know what that would be. Europa. We want to go down and see what, if anything, is swimming on those warm, salty oceans where they've been hit by comets for as many billion years as we have. They have the influx of amino acids that Earth did. Life started in Earth's oceans. And here's a body with warm, saltwater oceans that protected from all that radiation under maybe a mile of ice. Boy, do we want to drill or burn our way down there and see what's in that water. Unfortunately, the only probe on the drawing boards, and that's a European one, another ESA probe, and that's for years in the future, is only going to orbit Europa. Now, is anything more useless than orbiting Europa? No, we want to go there. So you asked me what I would like to see. That's what I'd like to see. We'd all like to see that, right? Okay, yes.
There's a chance if there is, there's guidance, there's talk of trying to capture some of that material as spectroscopic analysis. If they can find biomolecules, as a microbiologist, I'd interpret that as a very good.
Is he talking about 67P, the Rosetta mission? So I couldn't quite hear that, but you said something about molecules. You know, it's just a great idea. We love comets. Of course we love comets. And here, imagine you're on the surface of a comet. Perihelion's next August 13th. So between now, 67P is just going to get warmer and warmer. Currently, it's losing a gallon of water. Can we say gallons still? 4 liters of water per second. And it's going to grow to maybe 400 liters of water per second in just a month or two. So you're standing on the surface of this comet, and it's like manhole covers blowing up around you in some berserk city. You know, these vents opening up, geysers of steam, dust that was embedded in that, hydrogen sulfide, amino acids, and meanwhile you've got a spectrometer sniffing what's there, pictures, close-up photos. Boy, is this great. Great stuff. Okay, I have to leave. I can see from his body language that I have to leave. Thank you very much. Thank you.
All Thank you very much. Bob, on behalf of the Ottawa RASC and your many fans in Canada, we just wanted to give you a little token of our appreciation. It's a meteorite, and
Oh, really? That's very nice. Thank you.
we thoroughly enjoyed this. So once again, thank you so much.
Thank you. My pleasure.
Okay. Well, thank you very much again, everyone, for joining us tonight. I just want to remind everyone that this what you just witnessed with Bob is we have recorded it and we are recording it, and it'll be posted on the internet. If you Google Ottawa RASC and Ustream, it'll be you can find it there. We also will post it on YouTube, and I'll send out an email to everyone as well.
Yeah, the front page of the website as well, bro.
Terrific. Thanks. Chuck reminded me that we'll also have a link to the recording on the front page of our ottawa.rasc.ca website. Okay. Sorry about the audio problems, everyone. Hopefully we won't see that again, but cross your fingers. Next slide, please, Chris. Okay, we got two regular segments. Gary Boyle, our president and outreach coordinator, is going to talk about what to prominent objects in the December night sky. So, Gary.
Thank you.
Thank you.
Oh,
You took my.
I took your.
I did.
Took my shtick. Thank you, good evening, everyone. Could I have the house lights up, please? Just want to see all the first-time visitors here. Raise your hand. Oh, lovely. Great, great. Hope to see you more often. We do this once every month here at the Space Museum. Hope to see all these faces again many times, and hopefully you can give a presentation too. You're here because you love astronomy, and what I do every month is the sky this month, really what's up in the sky that you can see, hard or not hard, telescope, visual, whatnot, so we'll just get to it. So here we have Comet Lovejoy. Comet Lovejoy was discovered in August of 2014, and will be getting closest to the Earth on January 7th, where it'll be just a little less than half an astronomical unit, or about 70 million kilometers from Earth, so it's fairly far away. And the reason why we see comets is that when they come close enough to the sun, they begin to glow. And as Bob mentioned before, you get these geysers that come up, that shoots off a lot of material, you get this coma that forms, and then we can see the comet. Right now, 67P is not doing that, but when it rounds the sun, we should be able to see it again. Okay, next slide. So here's the actual track of the comet. If you have a telescope, you have binoculars, naked eye, but like I said, come January, it'll be a 7th magnitude. Here I can see down to 6 in the country skies, 7th, you will need binoculars, 8th, 9th, Pluto is about 14th. And when you get to the minuses, very bright, like Jupiter, the main planets, the sun and the moon. So we have the chart going up here, and it's coming out of the southern skies now, so you really cannot see it from this latitude. If you're down further, say in Florida, which we'd all love to be this time of year, you would then start to catch it in binoculars. Okay, next slide, please. Well, this month's constellation that focus on is Eridanus, the river Eridanus. And it's a very large constellation. Actually goes from the celestial equator, which is our own Earth's equator, but right down south to about -60, which we can't see. We can see about half of the constellation. And amongst the many galaxies, we have a planetary nebula. It has nothing to do with a planet, but it's the death of a star. It has this shell around it, which we can see faintly in telescopes, and does have a central star. And it has numbers. A lot of them, a few have proper names too. So he's about 6,500 light years away. It's in our own galaxy. But now these galaxies are extremely far away. In fact, this group is about 100 million light years away, very, very far. But still, you can see this with pretty well average to moderate-sized telescopes. So you don't really need the expensive $8,000 of equipment to look at galaxies in clusters. Some of the bright ones are even seen just with binoculars. So astronomy doesn't have to be expensive. It could, if you want it to be, just like cars. You can drive the cheapest car there is, or drive a Cadillac. It's up to you. Okay, next slide, please. On the night of December 13th into the morning of the 14th, the Gemini meteor shower, which I find is the best meteor shower of the entire year, will be, and people call them shooting stars, the general layman's terms, layperson's terms, sorry, not layman, layperson term, is shooting star. And really, all these is really the minute fragments or pretty well sand-sized particles that come off comets. But in this particular meteor shower, it's actually an asteroid, pretty well a dead comet, 3,200 Phaethon is its actual name. And as the Earth goes once around, just like an oval track, once we go once around the sun in our orbit, we encounter these clouds of material every now and then. And this is one of the best ones. As you can see, about 120 meteors per hour per single observer if it's clear. The moon should not interfere too much that night. And hopefully bundle up and check it outside. The great thing about this shower I like, not because of the cold, well, there's no bugs, first of all, no mosquitoes, but another thing too are they're very graceful. They shoot across the sky at only 36 kilometers per second. And the Perseids in August move about 72 kilometers per second, about 3 seconds from here in Montreal. So they're very graceful, some are very bright. If you can, stay up that night, bundle up, really enjoy the show. And you really don't need telescopes, binoculars, just look up in the sky, just your one power pupils. Okay, next slide. The winter solstice will be beginning in a few weeks, December 21st. In fact, it's at 6:03 a.m. Eastern Time is when the sun is at the lowest point on the ecliptic. And as you can see, with the Earth's pole over here, with Canada being up here, we get very, very little sun. In fact, that day we get about 8.5 hours of sunlight compared to the 15.5 hours of dark for astronomers, yay. And then after that, now the days get longer until we move up to spring, where it's 12 hours a day, 12 hours a night. And then during the summertime, we get 15.5 hours of daytime. So it's winter in the north and summer in the southern hemisphere. Yeah, universal time for those first-time visitors. That's what astronomers use to depict various events happening throughout the world. They couldn't really give a time zone for every time zone what this is, so they give one time, universal time, which is the old Greenwich Mean Time. For Ottawa, we subtract 5 hours. Next slide, please. Yes, now we have a couple of bright planets, one coming out, one out already. And you can see on the bottom here, I say screenshot from the iPhone 6 Sky Guide. Everyone has smartphones nowadays, and the apps that they have on these phones are just incredible. A wonderful way to start astronomy. So here's Sky Guide here. Wakey, wakey. And what it is, it's an accurate portrayal of the sky right now. So if we head outside to where this is pointing, we can actually look at the object in the sky. Constellations, you can click on a star to give you the information, whatnot. So there's a lot of astronomy just in these little phones. Of course, there are a lot of charts in Astronomy Magazine, Sky and Telescopes, Sky News here that's produced in Canada, Internet, heavens-above.com. A lot of good place to start astronomy. But of course, the best place is to come here. It costs nothing to come to our meetings, and you can ask any and all questions. We just love to entertain people. So here we have Venus slowly coming out of the solar glare. Where are we here? Hello. That was here a minute ago. Yeah, Venus up here. It's slowly coming out of the solar glare, so it's very close on the horizon when the sun is set in the western sky. So over the weeks and months, follow that very bright dot as it comes up in the sky until it gets about 45 degrees away from the sun. And just by what a degree is, a half a degree is the moon, the full moon at arm's length. So if you stick your pinky nail at arm's length, your nail's the size of the full moon. Don't do it at bus stops. You will get a free seat, obviously, if you keep doing this. Or don't use any other finger because you really tick people off. Okay, next slide. Venus is the second planet from the sun. And then we have Jupiter, which is the fifth planet from the sun, which is up in the sky now. It rises just around 10 o'clock. Here's our microphone again. It rises about 10 p.m. and is out all night long. Very bright object. Just the moon is brighter than Jupiter. Okay, next slide. And Jupiter, like I said, is large. You can fit 11 Earths across Jupiter itself. Extremely large, but it's very far away. Jupiter has about 40 or 60 really moons around in its orbit. But the 4 Galilean moons that we refer to can be seen with telescopes on any clear night. And over months, over hours and days. You can just see them orbit around. And through the Observer's Handbook, which has been mentioned already, we do have the ephemeris when you can see these transits. Such as, next slide. Here's an example coming up on December 23rd, where you have Io and Europa. The four are Io, Europa, Ganymede, Callisto. And Bob just mentioned Europa. That's the moon that we want to look for the little ETs. Well, over the course of about 5 hours, the two will drift across the surface of Jupiter and actually see the shadows, those little ink black shadows. If you've never seen it, very dramatic. You'll see it just like this for sure. In a telescope only, binoculars, not enough power. Next slide, please. Here's the monthly lunar phase. Of course, the hours when each phase is exact. I have the distance because the moon actually varies from in its orbit around the Earth by 50,000 kilometers, about 356,000 to 406,000. So this is why we have the wacko changes. And the cold moon is really tomorrow morning at 7:27. Cold is right, for sure. And this is taken from the Farmer's Almanac, such as the Hunter's Moon, the Harvest Moon, etc. Next slide, please. And also for the RASC, I also write the monthly article, the Sky This Month, which is on the national site. And you can find the links from our website, ottawa.rasc.ca. There's my website, wondersofastronomy.com. And please follow me on Twitter @AstroEducator. Next slide. And I'd like to take the opportunity to wish everyone a very Merry Christmas, Happy Hanukkah, season greetings, and a very healthy, prosperous New Year. Thanks. We'll see you soon.
Thank you, Gary. Next up is Al Scott. Now, normally we give him a 10-minute astronomy news update where he explores in more detail something newsworthy, but he knows I'm rushing him this month. So, Al?
Thank you, Mike. So yeah, we're on the clock tonight, so we'll make it quick. Next slide, please. So, as Mike has already alluded to, the interesting item of the month is the Rosetta probe. The Rosetta probe has landed a lander on this comet 67P Churyumov-Gerasimenko. Some sort of Russian name. Thank you. So comets, why are they interesting? Why would we send a $1 billion space mission to look at a comet? Well, comets are the building blocks of the solar system. They're primordial frozen ice and dirt blocks that have been left over from the formation of the solar system, orbiting out far from the sun in these reservoirs that we believe are out there, the Oort cloud, the Kuiper belt. And they contain a mixture of these organic chemicals, we believe, that may have seeded life on Earth, and they're pristine. They've been frozen. As they get perturbed out of their distant orbits, they come close to the sun, and now their volatiles that have been stored in these refrigerators for 4 billion years are now being released into the inner solar system and creating these meteor showers, such as the Geminids, and all the meteor showers, we believe, are from dust that spews out of these things as they evaporate their primordial payload. So what we want to do in this mission is to see what's there, to find out, are the organic chemicals there, the sort of things that we would think were on the early Earth, in the early oceans that came from these comets. The water in these comets, as they bombarded the early Earth, created the oceans and may have seeded life on the planet. Go to the next one, please. So this is the Philae lander. It's about the size of a washing machine, and this is the thing that dropped off of the Rosetta probe. Rosetta probe spent 10 years going through the solar system to precisely match its orbit to that of the comet, and then to slowly get closer and closer. The comet is about 6 kilometers in size on its longest axis. It has very little gravity. So it's very difficult to orbit it. You have to be very precise in your changes in velocity. And the thing is, it's about 400 million kilometers away, so it's like a half an hour of light travel time. So much of these maneuvers have to be done remotely, and then we find out whether they were successful a half an hour later. So this 100 kilogram probe as it comes down to the comet, on the comet it only weighs 10 grams due to the gravity of the comet. And so you need to make sure this thing lands softly enough that it doesn't bounce off and leave forever. And it almost did. Go to the next one, please. So here are the adventures of Philae as imaged by the orbiter, the main Rosetta probe. So it was supposed to come down, fire harpoons, embed itself into the comet and land. But what happened was it bounced. The harpoons didn't fire. It hit and it bounced off. And they said, oh, we've touched down, great. Turn off the flywheel that keeps us oriented. And what happened is that when they turned off the flywheel, all the angular momentum then started spinning up the probe because they thought they were on the ground, comet anchored in. So you can actually see they've searched the images and they've found this thing as it's descended, and they've found the touchdown point. Here's the area before touchdown. Here it is after. You can see this little dent, maybe a couple dents here or 3 dents where the feet touched down, and then it bounced off. And then it went on like a couple hours bounce up maybe a kilometer in the air over this thing and came back down. And you can see it here as it shoots off to its unknown landing spot, and ended up landing next to a wall a couple hours later in the dark on its side. Go to the next one, please. Here's an image from the Philae lander from 40 meters up as it's coming down for its first landing. The surface is covered by fine-grained dust and debris ranging from millimeters to meters in size. Go to the next one, please. These are images taken by Philae of its final landing spot. The surface, actually, you can't see very much up here. It's kind of dark, but you can see some what looks like a rock here. There's several scientific instruments on the probe. There's like a hammer. They can actually feel how hard the surface is, and they think it's like a few centimeters of dust, and then there's something hard underneath that, and they believe it's probably ice. It could be rock. But based on they know the density of the comet isn't as dense as rock, it's like ice. They've measured the temperature of the surface, it's minus 153 Celsius at the landing spot. They have a mass spectrometer, they have measured organic molecules in the vapor that's coming off of the comet. They have an oven that they've baked dust grains that have maybe fallen into the oven, and they've done some mass spec measurements, and they're reviewing that right now. There's going to be more results published later. They haven't actually figured out exactly where on the comet it is, but they're narrowing it down. There's several instruments that all gave data, and the scientific teams are going over this data right now. The problem is that because it's against the wall, it's not getting as much sun on its solar panels as they expected. So they're hoping that as the comet approaches the sun and gets close to its perihelion in August of 2015, that more light will come into these solar panels and reactivate the Philae probe so it can continue doing more experiments. But all this time, the Rosetta probe, the main probe itself, is still imaging the comet and watching from overhead and relaying communications. Every now and then it listens for the probe to see if it's still there. So it's a very interesting scientific mission, and I think there's a lot more to come out of this as we sift through all the science that's going to come out of these instruments. So thank you very much.
Okay, the next section is observation reports. Bruno, Paul, if you could make your way up here. I'm first going to share some observations that were sent to us from Mike Works. Remember, Mike Works was the fellow that generously donated the 18-inch Starmaster. So we had hoped that we could get a recording from Mike, but we had some sound problems. Go figure. So he sent me a script, and I'm going to read some notes from his script here. So Mike lives in a bed and breakfast. He's got a bed and breakfast on the Baja Peninsula, and can't remember. I think it must be 5 hours or 9 hours south of San Diego. He's quite remote. But in here, you can see his solar observatory that he built this past summer, and you can see the Pacific Ocean about 50 kilometers to the west. So he describes here that there's some wonderful winds that come from the ocean during the day, and that's why he gets some of the excellent seeing during the daytime, as you'll see with some of the solar photographs that follow. Next slide, please, your solar images. Next slide, please. Okay, so here Mike used a 152 millimeter hydrogen alpha solar scope. He's got attached to that a Grasshopper 3 USB 3 camera. He used a 2.5 times TeleView PowerMate, and he stacked it with AutoStack 2 software. Just amazing work here he's got. So this was the sunspot that he took from on June the 25th. This particular, pardon me, not sunspot, prominence. This prominence was the most interesting and the exciting, he says, of the whole summer. It was not particularly huge, but it was rapidly evolving and changing shape. It only lasted a half hour, but it was extremely bright, and he was fortunate to have captured this one in under 35 seconds. Next slide, please. Mike is amazing with his work here. This one here was taken October the 10th. He describes it as much more quiescent, a much more persistent shape. The seeing was very good. It allowed him to capture this prominence in quite high detail. He did overexpose to, as you'll see in the next slide here, to capture some more detail here. September 2nd, this was another active region. He describes it as the best seeing of all year. You can see details in the flow patterns, the magnetic flux lines, as he describes. It's very clear and in high detail. He stacked 400 to 500 frames to get this noise-free, very clean, noise-free image. Next slide. So, some of you may remember the partial solar eclipse we had, where the moon went in front of the sun. So you see that here. But what he describes is particularly interesting, and I guess this was September 23rd. What made this more memorable here was that he was able to capture, so the black image on the top there is the moon and going in front of the sun. What he was able to capture is some of the contours of the lunar south poles superimposed onto the solar disk there. So some of the contours he's describing are mountain ranges on the moon. So this is pretty impressive work on Mike.
Mike, you mean those bumps?
That's correct, the bumps. Next slide, please. So here is active region 2192, a sunspot group. It captured a lot of attention, and I understand, Paul, I think did it make its way all around the spinning sun?
It did.
It did. So this is one that persisted for over 28 days, I believe. And it was the biggest sunspot group I think any of us can remember in a long time. But again, amazing images from Mike. Next slide. So this is an image that an image that he actually took from the web here, but just to give you some idea of the scale of sunspot group 2192 relative to the size of the Earth. So if you were to put the Earth against it, you can see that you can put many of the Earths side by side. It was a big sunspot group. I think that is it. Okay, next up is Bruno. Bruno was up here last month. He introduced himself, and just a brief introduction to yourself, Bruno. He's a student from Brazil. Thank you, Bruno. And he did some imaging in a remote location. I'll let him explain it. But we had the pleasure of meeting him, and as you'll see, he's a very charming young man. Bruno.
Bobby Berman is outside, but I'd like to thank him once more for his brilliant speech. Thanks.
Thank you. I'm here. Thank you.
Thanks. Thanks, Gary. Thanks, Coach. Thanks, Mike. So, good evening, everyone. It's a pleasure for me to join this meeting with you tonight. And I'm glad to have this opportunity to share some experience that I had a few weeks ago. I'm going to show you something really special, but first, I will briefly describe myself. My name is Bruno Favoreto Silva, and I'm a Brazilian student taking civil engineering at Carleton University. And I'm here through a scholarship program offered by the Brazilian government called Science Without Borders. This program allowed me to study here for 1.5 years, in which I had the opportunity to study English for 6 months. I had the opportunity to take 2 terms of civil engineering at Carleton University, and also I had the opportunity to join a research group at University of Ottawa for 4 months. And since I came to Ottawa in July of 2013, I have been traveling around Canada, US, and Mexico. And 2 weeks ago, specifically, I spent 4 nights in Whitehorse, the capital of Yukon Territory, the biggest city of all Canadian territories, with around 28,000 people. And I was there for a dream. A small word that has a special in our lives. Everybody has a dream. And you have a dream, if you have a will, if you have a goal, which I know you have, take a pen, take a pencil, write your dreams in the paper. Don't let them die in your imagination. Try to figure out the best ways to accomplish them, because your success is related to how big are your dreams and how willing you are to accomplish them. So, I was in Whitehorse for a dream. I was in Whitehorse for the Northern Lights. I spent 4 nights there, and every single night we drove north from Whitehorse downtown in order to avoid the light pollution. We could stay in the middle of the jungle, in the middle of nowhere, only with the light of the stars and the light of the cameras. So I'm gonna show you a video that I did, 1 minute time-lapse video, which has a real life of 4 nights. And I was analyzing the skies, the stars themselves, and I did this time-lapse with a camera Canon T3i with lenses set up on 18 millimeters with a long exposure time of 30 seconds and a gap of 10 seconds between every photo. So every 40 seconds I got a new photo. So I want to share this experience with you. If you could please play the video. So I'd like to thank once more Mike and Gary and Chris and Paul and everybody who gave me this opportunity to share this experience with you. And I hope you enjoyed, and that's it.
I've added a little time lapse in at the end to explain that little anomaly.
Oh, okay.
Of course.
Do you have time?
Yes. No, but do it anyhow.
Okay. The last video, these images. It's a very good question because I have been looking for the answers for a long time. I have talked to the Department of Science of Carleton University and University of Ottawa, and that's how I got the contact of Gary Boyle. And for the first moment, I couldn't realize what was going on, because we were inside a cabin talking to each other. We were in a group of 10 or 12 people, and we were waiting for the Northern Lights. This night itself, the lights didn't show up, but I had set up my camera to take photos every 40 seconds, as I previously said. But I was talking to the people inside the cabin, and I was looking into the direction of the door when I saw a flashlight in the sky. And then I ran into the door to see what was going on, but I couldn't see anything. Nobody could explain that, and then I realized my camera was on, so I waited for the end of the time lapse to see the photos and to analyze them. And the guides who were there with me saw the photos by that time, and they couldn't answer for sure what was going on. So from that time on, I have been asking many people to see what's that, but I met Paul, and he could explain everything for me. It's like an airplane that comes from the east to the west, and as you can see, there are 4 images, which was weird for me by that time because, like I said, every 30 seconds I had one photo, so this movement lasts 2 minutes, in which we couldn't see anything. So for me, it was really weird. But Paul analyzed these photos by himself, and he could tell me that he was almost sure it's a plane, like for the geometry stuffs and for the lights, because in the left side we have green color and the right side we have red. And this 12 dots means the light that the plane shows in the sky, like every how many seconds, I don't know. But Paul knows how to explain more than me. So, but until that time, I couldn't know what was going on. But it's not an UFO or anything like that, it's just a plane. Yeah, that's it.
Thank you again, Bruno. Thanks for looking us up. And Bruno, if your parents are watching this broadcast, just to tell them, they have a fine son. Don't you agree? Sure, if you want.
Okay, I would like just to thank my family and for my friends that are watching online from here and from Brazil. And thanks everybody once again for paying attention to this video.
Thank you, Bruno. Actually, that mystery object that we were talking about at the end there, it was really fascinating, the discussion that Paul, Bruno, myself, and Paul Clounger examined it, and Paul did all the heavy lifting, and his analysis of this is fascinating, and it's worth having a presentation on it, and I'm going to twist his arm to do it in a future meeting. Up next, Paul Clounger.
Thanks, Mike. Sorry it wasn't a UFO, Bruno. If I can't have a UFO, you can't have one either. I'll explain that reference to you later. Hi, everybody. I've got just a few slides to show you. Last month I showed you this lovely sunspot group that we had gracing the sun, largest one in 25 years. Almost exactly a month later, in other words, just on November the 21st, I managed to image it again. It did survive its passage around the sun, and when it came around, next slide, Chris, you can see where we are. So you can see it's much smaller than its previous apparition, and certainly much less active. But it did survive, and I don't think it'll make a third trip around. But anyway, that's our sunspot. Also redesignated AR 2205, I believe. Now we know when a sunspot goes all the way around the sun and survives for a second passage. In the past, we didn't know that, so. Whenever a sunspot came around, even if it was the same one, it was always given a new designation. So 2192 on its first pass, 2205 on its second pass. All right. So something a little further afield, and you guys thought I was joking at the dinner when I said, let's step it up here because I've got imaging to do. It was clear that night, remember? Well, as it turned out, it was the only clear night I've had in the last 2 months, so I actually did go out and do some imaging. And so this is one of the things I captured. This is M108 up in Ursa Major. It's a barred spiral galaxy about 46 million light years away, and managed to bag this after the dinner, after feeling good with the dinner. This was a combined shot of 21 minutes with the 11-inch Edge HD. So going a little further afield, I continue my fascination with things that are very distant and kind of obscure. A while back, some of you may remember that I showed you Hoag's object. This is not my image, unfortunately. This is from the Hubble Space Telescope. Hoag's object is a very distant galaxy. It's a rare kind of galaxy called a ring galaxy, and extremely distant. This object is 600 million light years from here. So when the light left this object, life hadn't even crawled upon the dry lands of the Earth. So just to give you an idea how old this is. And what's really spectacular with this image is that these types of ring galaxies are really quite rare, but this is a really particularly rare one because within the ring itself, look at that, there's another ring galaxy. So if these are comparable in size, and this is 600 million light years away, this guy's got to be on the order of 6 or 7 billion light years away. It's quite a spectacular catch to find two face-on ring galaxies in that kind of an orientation. So very cool. So I've been fascinated with this object for a while. I did image it a couple of years ago with a smaller telescope, but this summer I actually managed to get my 11-inch on it, and I got this following picture there. You can see.
Oh, wow.
You can see the ring there, and thank you. Just a fascinating object. Yeah, this was quite a long burn. This is about 3 hours worth of exposure with the 11-inch and with a monochrome CCD camera, the QHY9. So very, very distant. And
If I could intervene from, it's a real shame with lights in the auditorium.
yeah.
On the computer, you can see the whole ring around that galaxy.
Why don't we turn them off? Turn off the lights?
If you can, yeah, it's a low contrast thing. I didn't want to exaggerate it. I want to try to make it look realistic, but there you can see the ring.
Turn it off. Off.
Yeah, there you go. It's just a fascinating object there, and I guess you remember this one, eh, Gordon, from our first attempt to find this.
And based on your photograph, I'm amazed we saw what we did.
I am too, actually, to be able to. Gordon and I first saw this object a couple of years back out in the burnt lands, not far from FLO, and he's the one that actually put me onto it. And we could actually see this object through the telescope visually. So to see a galaxy 600 million light years away visually was a real treat, and so it's been on my mind since then. And I finally got around to getting some good shots since I got the observatory set up at home, because you needed a long burn for this, and it's best seen in the summer when our nights are short, and so our opportunities to get long exposures or long runs is a bit limited. This is in fact imaged over a couple of different nights, so I could accumulate enough data to produce the image.
Which constellation did it fall?
That is in, I have that. Serpens, yeah, it is actually in Serpens, you're right. So yeah, a treat of an object. Thanks, Gord. So my last one here is this little guy. I shot him hanging around my backyard. For those of you, some of you know this, when we do observing out at my site there, it's about 20 kilometers further west than FLO. The barn owls will actually talk to us at night. They come out and they sing their song, and we sometimes talk back to them, depending on how many beers we've had. But yeah, I actually saw him in the daytime, and yeah, he was right in my backyard there. So I thought this picture was appropriate because the second target that I shot was this one. So that's the Owl Nebula again after the dinner 2 weeks ago. Actually, if you can dim the lights on that one too, because it's a little faint. There you go. Yeah, there we go. So yes, the Owl Nebula, M97, also an Ursa Major. In fact, right a stone's throw away from M108, the galaxy that I showed previously. So this is a planetary nebula. It's about 2,000 light years from here, and and it was actually formed about 8,000 years ago, our time there. So thank you very much for listening. I hope you all have a great holiday and a great New Year, and we'll see you here in January. Take care.
Thank you, Paul. Just real quickly before as we're moving on here, I'd like to say a few things about membership benefits here. As members in the RASC, the Ottawa Centre, we do have what Paul referred to as Flo Fred Lossing Observatory. It's an observatory for our members. We have a telescope loan library, so with your membership, you can sign out telescopes, much like you would sign out a book. There is a $10 charge for each month, but it's a great opportunity to try before you buy. We also have, as well, we have With the membership, you get a wonderful observer's handbook, as well as a yearly edition to Sky News Magazine. We also have an astronomy library, a book library as well, which has an extensive collection of astronomy books that you can take out for month after month. And in addition to other journals and articles and so forth, one adult membership is in our center is $72. A family membership is $67 is the base charge. First adult is $77. Second adult is another $10 on top of that, or $5 for a youth. So family membership is the way to go, obviously. With your membership dues, it brings in wonderful speakers like Bob Burnham, and I'm really keen on doing a lot more of this kind of thing and maybe expanding our meeting. With some of the other things we're doing with membership is, or with our center is we're offering telescope clinics. Paul's going to be offering an imaging and video astronomy clinic. We're planning to do that in July if all works out well. And Chris, what we're showing here is some of the other benefits of local benefits and national benefits. So we think it's a wonderful deal. If you are interested in membership, you can actually buy it here tonight, okay? And we can sign you up and get you going here. But I'm pretty convinced there's a really good value here with membership. Club information. Here are the contacts if you wish to. And also, by the way, we also do have discounts for Sky and Telescope and Astronomy Magazine. That URL you see at the bottom there, the tinyurl.com, RASC Ottawa with the block letters there. That's if you want to find out more about if you're a member or if you're considering membership and you want to contact somebody about membership benefits. You can get access to folks' email and ask them questions and so forth. Our library, our astronomy book library, is in the Science and Technology Museum. Most of you know that the Science and Technology Museum sadly has a problem with mold and other things right now. But
And the ceiling.
and the ceiling, I guess, as well. So, but by the way, the Museum Corporation was very kind enough to put us into this facility, and they did it flawlessly. So I very much appreciate that. After the meeting, we have a social get-together. Everyone is welcome. It's at Perkins Restaurant, which is at Saint Laurent and Ogilvie, and it's a nice location. I mentioned earlier, if you want to watch this broadcast, it's Google Ottawa RAC and Ustream, and you will see it minutes after this after tonight. And it's also will be posted at some point on YouTube, again through the link that Chuck mentioned on our main webpage. I think membership numbers, I gotta believe we're over 200 tonight. Wonderful attendance. Thank you all for attending. We have a number of volunteers, okay, tonight that quietly worked away weeks in advance and tonight to make this happen. Thank you so much. Really did a fine job. Next meeting is Friday, January the 9th. We typically meet the first Friday of every month. It is free, and everyone is once again welcome to join us. This one here happens to be the second Friday of January. Next slide. And we have two speakers. Rick Wagner, you may remember Rick is everyone knows Rick is very methodical and very detailed. You remember his previous presentation only a month or two ago. Rick is going to talk about polar alignment, okay, looking at it very closely, and some of the techniques. I'm trying to sort of gear some presentations to some of the newer members that when many of us went through the polar alignment process, it can be a frustrating one. Rick's going to do a thorough analysis of when you want to use what technique and so forth. Gordon Webster is going to be talking about our Fred Lossing Observatory, okay, our members' observatory and what it has to offer, and some plans actually for the future as well. Okay, well, everyone who's on the webcast, thank you for joining, and again, you can always come and visit us in person, but thanks for joining us. Thanks.